Today we're going to talk, let me go back a little bit. Today's agenda, we're going to cover block diagrams, block diagram algebra, how transfer functions play into that, MATLAB response. We will end up using our computers today to run a simulation in Simulink, which is all about block diagrams. You remember LabVIEW? You did LabVIEW in instrumentation? So you connect little things. This is basically that, using math operators, stuff like that. So a block diagram is just a pictorial, graphical representation of a system, and these could be very large, very, very large diagrams showing how everything connects. Simulink and LabVIEW use block diagrams to construct programs. Again, it's kind of nice to see everything mapped out, like what goes into what. So how it works is each dynamic system or component is a block, usually a transfer function. Then you connect them by signal paths, input, output signals, and usually any arrow. So we're connecting blocks to with arrows. The arrow represents, if it goes into a block, that's typically multiplication. I'm taking this input, multiplying it by this block, and now I get an output. And a lot of times there's feedback loops. So I especially for the class after this 480, you're taking some kind of output, you're sending that signal back to your PID controller to go, okay, we're here, we want to be here, so how should we affect the outcome, knowing some of that sensor information coming at the end. So typically, any kind of dynamic system, if it is single input, single output, you can represent it by a transfer function. That is just a block. And so in Simulink, they have a transfer function block. And it looks like that. So the signal input goes in, that's U. That gets essentially multiplied by this transfer function, which it's in the S domain, Laplace. And it gives you your output Y. So just as a recap, like if I have my mathematical model, I create this input-output equation that looks like this. I can create the transfer function. And then in my block diagram, I send my input in. The output is there based on that transfer function. So we can look at velocity, position, if it's a mechanical problem, or any real problem. It could be circuits, hydraulic, whatever. So that's just what the block looks like. That's in MATLAB. There's a few other blocks. So this is for Simulink. Multiplication, if I want some kind of gain, I can just have a multiplier block. Now, typically, actually, it's a triangle. So gain is typically represented by a triangle. So let's just say I have an input of 5, and I want to just put a gain of 2 on it. So that's 5 coming in. Inside the triangle is 2, and the output is 10, right? So that's really how these blocks work. It's usually a multiplier of whatever that input signal is. But there's other blocks. I can have an integrator block. All three of these mean the same thing. Either I'm taking the integral of the input, so y is just the integral of that. We have 1 over capital D, 1 over S. These essentially mean the same thing. Now, you may have never seen the capital D operator before. That is used in the textbook every now and then. It's the same thing as S. It's just like in the time domain. So I just like to use this one. So anytime I want to take the integral, I can just put it through this block. So you divide it by S. That's essentially the same as taking the integral of that input. If I wanted to take the derivative of an input signal, what would that block be? Just thinking about it. If 1 over s is the integral, then the derivative would be I guess we'll never know. Oh wait, no. Derivative would be just a block of s. Because remember, dot becomes s, the derivative. So s is essentially the derivative with respect to time. So if I multiply something by s, that's taking its derivative. Y dot is the same as s times y. Maybe understand. Okay. So those are some. Now, one that we definitely use is the junction block. So a summing junction adds or subtracts signals. Note, we've had a lot of different equations up to this point where I can't necessarily make a transfer function from it because I have multiple inputs or multiple outputs, something like that. This is can be used to basically combine some signals and then send it through a transfer function if I have multiple inputs. And so you can have this for as many as you need. So in MATLAB, you can set, I have 10 inputs. 5 of them are positive, 5 of them are negative, or whatever. But the output signal in this case, if I have a plus and a minus, Y output equals U minus W. And so it'll ask you for the signs there. Okay, this is definitely useful when I have a feedback loop. So I have something coming from the back to the beginning. We can use this summing junction to combine those signals. Let's talk about algebra, everyone's favorite type of math. First off, there's often more than one way to represent a system using a block diagram. So let's just say I have my typical system. This is a first order system right here. I have x dot plus 7x equals my input force. Let's say it's a mechanical system. I could rewrite it. So I could move the 7x over here. I could take the integral of this. That would really be in parentheses like that. So I could rewrite it as x is equal to the integral of my input force minus 7x, function of time. So there's two ways that I can draw this. And which one do you like better? Do you have a preference? Neither? Which one looks a little simpler? Just thinking about it. I'll tell you which one I like. I can make a transfer function out of this real fast. This becomes s plus 7. It would be 1 over s plus 7. That's my transfer function. So that would be right here. So my input force comes in. It gets multiplied by the transfer function. That gives me my output x. I like that. Anytime I've got a CISO, and I have a way that I can package that up so I get this transfer function, even if it may have multiple inputs, this is always the way to go in Simulink. But this just shows you that, if I rewrite it, if I rearrange things, I can also write it this. And basically, what this shows is that a transfer function does have a feedback loop. This is a first order. If I had second order, I could have two different feedback loops going into it, where again, the output is x, the input is the force, but what we're seeing is that there is some feedback based on how the position is. That's informing the system based on the inputs of how the system will change from there. So I like this one a little bit better, okay? Anytime you can create a transfer function, try to do that. because Simulink has a transfer function block. Now, block diagrams obey the rules of algebra. So we can simplify, we can collapse block diagrams using algebraic rules. Just remember that if I send an arrow into a block, that's essentially a multiplier. Even if it's a transfer function, I'm multiplying whatever that input is by the transfer function. So let's say I had this force gets multiplied by T1. That gives me an output of B. And then I take B and I multiply it by T2. That gives me X. We don't have to keep it separate. If I don't really care what B is, any two blocks connected in series, we can just multiply together. So it's just like, forget about B. I just want to figure out the relationship between F and X. So two transfer functions in series, you just multiply them together. And we've talked about that before. That's just a visual way to see what's going on. Now this one's a little more complicated. I have a force coming in with a negative feedback loop. That goes through a transfer function, gives me my output. So we can take this and we can get, instead of that complicated, if I want to just combine it all into one transfer function, it is possible. That kind of looks like, if I go back a slide, a little bit like, I wanted to go back a slide, here, right? I've got that negative feedback loop. So that's kind of what's going on within a transfer function. So I can take those same rules and apply it to here. Let me break down this for you. How can I get from this schematic to this schematic? Well, it's algebra. So for example, A, how could I write A? So I'm working on this. I want to figure out how I can get that transfer function. What is A equal to? Well, I have a summing junction right here, so that's going to be a positive F minus B. So A equals F minus B. Everyone following? Okay. What is B equal to? What would you say B is equal to? Very good. It's going to be G times H. So G times H. What? Where'd you get the G? Oh. I should have checked it before I just wrote it down. B equals, let's see, this is my signal B. There is an H, but what is H multiplied by? What's the arrow going into H? It's not G. It's X. Yeah, so it's going to be B equals H, which is a transfer function, times my output, which is X. Okay. So we can change this to be A equals F minus H times X. I'm not quite there. What I want to get is output is X, input is F. So I need to figure out what is A, how I can rewrite A. What is X equal to? If I work backwards from X, X is equal to G times A. So that means that A is equal to X over G. So we can say X over G is equal to F minus H X. So now I at least have, so G and H are going to stick around. They're two transfer functions, but now I've gotten rid of A, which is kind of inside the system, and now I want to just rearrange this. And so we can multiply both sides by G, so we get X equals GF minus GHX. I can add those x's to the same side, so I got X times 1 plus GH equals G times F, gluten-free. And then if I want my output X over the input F, I'm left with this. So that just shows how I can take, that's just the algebra going on, how I can take two transfer functions with that negative feedback loop and actually combine it into one transfer. Questions? They're multipliers. Blocks, arrows going in are blocks. The only thing that's not a multiplier would really be the summing junction, where you have positive, negative, so you're just adding stuff up. And then it's all algebra from there. We've already done a bunch of algebra, haven't we? You take some equations, you can put them in the S domain, you can move things around. That's what this is. I can have multiple parts that connect to each other, and then we can simplify and, take 4 different equations, actually get to one transfer function. Same algebra going on, just a different way to look at it. Some of you might like the visual representation. I tend to like it. Again, for more complicated systems, you can really kind of follow, okay, what goes into what. Good? Just remember that there is more than one correct block diagram possible. So it depends on, what is our variable of interest. And we all kind of see things differently. So if you, draw it slightly different, that's totally fine. We're not all going to have the same answer, but hopefully it does at least match up with the equations. Okay, I'm going to do an example, and then you're going to try a problem. Let's say we have I've done body. I don't know what this is. Maybe it's a mechanical system because I got a force, I have X, but it really could be any kind of system. They tell us the output is X, and we have 2 inputs. So it's not just going to be one simple transfer function. I've got 2 inputs, F and G. And one other thing is they're telling us they want to indicate the location of Y on the diagram. That may be an important part. Maybe that's like something we want to be checking, like a sensor or our SSR. So we've got our 2 equations. X is the output, F and G are inputs. One thing I can do just to start is, I know I have 2 inputs. Typically, we read from left to right, so I'm going to say this is my input F, function of S. This is my input G as a function of S. And this is my output. So I'm trying to, using the equations up there, is to fill in the rest of this. Pictorially, how are these connected? Where is Y located? I don't have my notes. I forgot how to do it. Any suggestions on what we should do? Solve the equations for G, like what is G equal to? Okay, we could, yeah, because we could definitely move some stuff around, and then maybe work our ways back. I like the way you're thinking. I think sometimes for me, what I like to do is I like to actually start at the end and work my way back, because I know what my output is. So it may be easiest to solve for x and then eventually get to my inputs f and g. But if we're doing block diagrams, we're doing algebra, this is in Laplace, we're using S. So really the first thing I want to do is take these into the S domain. Just like if we were making a transfer function. So dots become S's. So we get S times my output X is equal to Y minus 5X plus G. So I'm just going to take my time domain equations, change them into the S domain. This will allow us to do the algebra. Same thing for the other equation. We have S times Y equals 10. Now my force, we turn it into the S domain, 30x. Okay, are we closer? I'm not sure. Are we closer? What we can do is get all the x's to the same side. So we get S plus 5 times x is equal to y plus g. Yeah. Like I said, I like to just try to solve for x. So with this one, it becomes pretty easy. So now I've got x. I'm going to divide both sides by this. So this is essentially a transfer function right here. 1 over s plus 5 times, I have two inputs, y plus g. So that means that x, my output, which is on the right-hand side of my diagram, is equal to, when I have a 1 over s plus 5 times combination of two inputs. Okay, so what that means is this becomes my transfer function, which is just a block like this. That's 1 over s plus 5. That's the transfer function there. Now we have two inputs. So that means I've got a summing junction. I have a positive and a negative. This is going to be y. So y plus g. So actually both of them are positive. Like that. So x is equal to 1 over s plus 5 times the combination of y plus d. So we can take our complicated systems, and this is not that complicated. We can go to much more complicated systems, and by setting up these equations, how things relate to each other, we can put together a pictorial representation of how it's flowing from these inputs, left-hand side, to the output, right-hand side. But now what do we do? I got 1/2 of the system. I left off on y. That needs a connection. How can I solve for y? Is it pretty easy? Do I have a y in the other equation? How can I isolate y? can divide both sides by s. So we have 1 over s times 10f minus 30x. So y is equal to 1 over s. I can just put a block here. Again, that's just a transfer function. It's about as simple as it gets. First order transfer function, that's an integral. So y is equal to 1 over s times 10f minus 30x. This is another summing junction where we're going to have 10f minus 30x. So we're going to put some gain on that input of 10. That's coming in, that's positive. 10f minus 30x. X is my output. So we're pulling from here. We're putting a gain of 30 on it. Then we're subtracting it. Now, is it possible to simplify this? It may be possible to simplify some of the things going on here. But it is a little bit trickier. If I just had one input, if I just had an input of f, I should be able to pull all this together into one transfer function. But with the two not being added at the same place, you know, there are different parts here. That's where it gets a little more complicated, where this allows me to group it all together, just like an SSR does. Just two different ways to kind of see how the system is operating. And again, this is similar to LabVIEW, making some of those connections, doing some of the math operations, to be able to take, you know, certain signals and change them into different types of outputs. Question. So first thing, taking into the S domain, I would solve for the output first and kind of work your way back until you get to both of those inputs. All we've got really is gain, any kind of multiplier. We have summing junction, and then we've got space for transfer function as well. Those are like the three main things that you'll use to combine some of these systems. Cool. All right. I'm going to give you an example. No, I'm going to give you a problem to work on right here. I want you to draw the block diagram. This is actually easier than my example. It's rare. I want you to just try to get some practice of putting together a block diagram representation. And if you have any questions, let me know. Step one, get it into an algebraic form. Laplace transform. That way we can combine some of these variables, simplify it, no more dot. Oh, it's going great. Make sure they don't break it, okay? Make sure they don't break it. All right. You'll keep. That's good. I never liked that machine. Uh, You don't get it? Almost all the X's combined. Again, we've got two inputs, so we can just draw it the same way here. We got F, we got G, and then on the output side, we have again X. So we're just trying to fill in the gaps here. How do these connect? How can I visually represent what's going on? And again, just like the last problem I did, I would solve for X. That's my output. So once I have my equation like this in the S domain, let me move some things around, solve for X, and then I can work my way from right to left. So we just divide both sides by that polynomial. That essentially gives me a transfer function. I just have two inputs, or a combination of two inputs going into it. Who's got a diagram? Oh, you work? You got one? Wait, who? So you have the same arrows. There it is. It's coming together. X. There's my block diagram. So again, setting this one equation equal to X means that X equals transfer function 1 over 5s squared plus 3s plus 7 times the combination of 10f minus 4g. So the summing junction allows us to get all that together, basically package it up into a single input to the transfer function, which gives us our output. In this case, we didn't have any negative feedback loop, anything like that. So this one really couldn't be simplified anymore. It's just, based on what we've done, we wouldn't really be able to make a transfer function, but unless we, have both of these two inputs together. So this is the way that we can visually represent what's going on. Questions? And it takes a while to get the hang of it, but just knowing that everything's basically a multiplier, right? besides the summing junction. Everything's a multiplier. And so getting into the S domain, we can just use algebra to set up these equations. Do I have another one? I forget. We can go backwards. So transfer functions from block diagrams. So I know we just covered block diagrams. I can take an equation and create a block diagram. If I gave you a block diagram, could you find the transfer function? Maybe, perhaps. It's algebra, right? It's just another way to look at it. So again, it's kind of up to how you see the problem. So we might get slightly different equations if I do it compared to you, but trying to, at least for my case, I always like to try to find transfer functions first. Those are pretty easy. If I can package things up to a transfer function, but it's really just following the arrows, setting up some equations, going from there. So let's say we've got this transfer block diagram here. And this is a pretty standard way to represent a system. This could be mechanical, but again, it could be really any kind of system where you may have some kind of feedback loop like this. And if I don't really care about like Z or Y, I really just care about the relationship between the global input F and the global output X, we are able to take this complicated looking system and change it into one transfer function. How do we do that? Now I could do what I just did a few slides ago and like, okay, Z is equal to Y is equal to X is equal to, you can set up basically 3 or 4 equations, kind of substitute in there and we'll get to the same answer. But anyone remember what we can do if we've got 2 transfer functions in series? Almost. It's not like resistors. So it's not adding them, but it's multiplying them. So what we can do is we can simplify this. So here's F. Here's my junction right here, plus, negative. We can actually multiply these two together. So there's just a 1 on top. And I've got an S squared. And then I've got a 6S and a 12S. So that's 18S. And then I've got a 6 times 12, which is 72. Now we still have this feedback loop on my best 8. We still have this feedback loop, so I don't quite have the full transfer function yet, but we're almost there. But anytime I've got 2 transfer functions in series, I can just multiply them together. Series. Now I've got the feedback loop. Now, we just went over what happens if I have a transfer function and a transfer function down below. You can combine those. So for example, I think it would become the total transfer function would be, if I call this G and I call this H, it should end up as G over 1 plus G times H. I think that's what's going to happen. You don't have to memorize that. We're just going to follow the algebra right here. But we should be able to make one transfer function. So for example, x is equal to, if I call that g, this is g times a combination of f minus, I'll just use 8x. So x is equal to, here's s squared plus 18s plus 72 multiplied by f minus 8x. Again, I like to start at the end. X is equal to this times the combination of f minus 8x. So everything's basically a multiplier besides summing junction. Hey, what are we going to do next? Well, let's get all the x's to one side. So x, we have 1 on this side plus 8 over s squared plus 18s plus 72. This is equal to 1 over s squared plus 18s plus 72 multiplied by the input s. I just added that to both sides. We can combine these. So 1, if I multiply it all by that denominator, this is s squared plus 18s plus 72 plus 8 is 80. So again, what I'm trying to get to is just one transfer function. So our goal is to just, here's f, here's my transfer function, and here's x. Just trying to get to one transfer function. So now I've gotten to a point where this cancels out, this cancels out. And so if I'm trying to find x as a function of f, x over f, that's going to be 1 over s squared plus 18s plus 80. That would be my transfer function right there. Notice what it did. All I really did was I had my initial transfer function with that negative feedback, okay, which is 8. I just took the 72 and added 8 there. That's all that happened. Because that's using the x. There's no derivatives. There's no s's tied to that. And so that's really how it came out. So if I wanted to check it, we could look at it this way as g over 1 plus g times h. That should give you the same equation as that one. So anytime I've got that negative feedback loop, I'm really just kind of adding to the denominator, changing that up. This might be nice to do. It could be fine just leaving it like that, you know, having it all spaced out in case I wanted to get like a reading of, well, what is y? Like if I'm going from this step to another stage, different part of the system, maybe I want to keep that separate just so I can check on everything. We could put a scope on each part just to see where it all is. How are you feeling about the algebra? Can you follow the lines? Is it making some sense? Okay. Let's see. Uh, you know what? Let's do one more together. I'm going to do this one real fast. And then I'm going to give you a problem to do involving the DC motor so you can create a block diagram from it. Let's, we want to find C as a function of R from the given block diagram. How is that possible? We got D in there. You know what? I'm just going to skip it. I think you just have to set D equal to 0 at that point. So this could be good practice. I think I want to give you a more realistic one like we've done in class. Here's the problem I want you to try. We just did an SSR of this last time in class. SSR is one way that I can represent a system. Matrix, vector, stuff like that. Block diagram is another way. I want you to create a block diagram for the DC motor. So this is going to connect everything. It's all going to be one large diagram. You want to figure out what is your global input, what is your global output. Then you're going to maybe make some connections, make some transfer functions to get from one to the next. All right, so I'm going to give you some time to work on it. If you're not sure where to start, can someone help? What's a good place to start? Breathe. Oh, if I was doing SSR, yeah. But right now, I just want a block diagram, so you don't need to do state variables. I would say dots to S's through Laplace transform. Get it all into a nice algebraic, because that's what the block diagram means, algebra. And then also trying to figure out, okay, for my diagram, what's on the left, what's on the right, like what's powering this thing, and what is the like final output we're looking at. Let's say there's En, there's a load torque, and on the outside, this is omega, or rotor velocity. Oh, all the way back to these two inputs. Yeah, hopefully. I wonder if I. Oh, no, that's not what I want. For that, KB and KM are the same thing as the back EMF constant. So I'm just going to use all KB there. We have En, and we have load torque. And then at the end of this, we've got our rotor speed, which is omega. So, as I've said a couple times, what I like to do, and you don't necessarily have to do it this way, but I want to solve for my output omega, which is going to be 1 over Js plus B times combination of KB current minus load torque. So if I can get that of like, here's my global output, here's my equation for the global output. Now I can start at the right-hand side of my block diagram and start moving to the left. So omega is equal to 1 over Js plus B. That's a first order transfer function. I can put that right here. 1 over JS plus B. Good, it's that times I have a combination, I have a summing junction. So this is going to be, I'm going to have a plus, I'm going to have a minus. Load torque is just going to come all the way across. And I'm going to have a multiplier KB times my current I, which is a variable. That's not a block or anything like that. This is just current coming out of the system. So this is the first half. Omega is equal to 1 over JS plus B times KB times current minus load torque. That's one of my equations. Now I'm going to pause here. You can fill in the rest. I'm going to give you a little bit more time. Okay, now that I've got that first equation down, let me try to put the second equation in. I left off on current, I. You should be able to solve the other equation for I, and then kind of work your way back just like this one. This will have a feedback loop because as the motor turns faster and faster, there's more voltage back EMF, which is going to reduce the current. And if you have questions about what I just did, let me know. Oh, I thought you were raising your hand. Everyone's cool. It's good. Anyone kind of like the pictorial representation? Yeah. Again, this is one method. SSR is another way to kind of package things up. And MATLAB understands both ways as well as others. So like for the upcoming lab 2, you can kind of decide how you want to represent your system to be able to solve for something. Yeah. Yeah, so it's going to be 1 over LSR, but then it's going to be En minus KB omega. So the omega has to, you're going to have a feedback. Oh yeah, it goes all the way from the back and around. Yeah, yeah. We will have a feedback loop. We're going to pull from that omega. So I is equal to 1 over LS plus R times, I have a combination. So I'm going to have a En that's positive. I'm going to have a negative KB times omega. So we're going to get that feedback loop going. So that should complete our block diagram. So now, if I know what En, what my load torque is, if I put all these values in, and I can specify these in the MATLAB script. I can put them all in the script, and then the block diagram, it can pull from those values, and from there, I can give it an input voltage, a load torque, and it should spit out what that speed is as a function of time. Now, some people ask me, we have the same KB here. Is there a way that we can combine those? There may be, but I think this is totally fine. because I'm using it for different variables. So I would just keep them separate like this. But it has been brought up before. If there's a way to, I don't know, like go across it, use the same constant. But I think the best would just be keep it separate. So now we've looked at it to the same problem two different ways. We have a block diagram, we have an SSR. And both of them, if I set my inputs and I have it all set up, MATLAB will be able to solve it. That's what we're going to do in the second half of class. Speaking of second half of class, let's see what I have next. We're going to talk about MATLAB after we come back from the break. I'm going to leave this up here. It's 8:09. Come back at 8:14. What I want you to have is your computers up with MATLAB. Now, I think under the class resources, I have something called a MATLAB code sheet. You'll also want to pull that up. It should be under Halo class resources. So you can pull that up, have MATLAB up, just MATLAB for now, and we'll go through some stuff in a few minutes. This is like making parts to show. Wow. Okay. That sounds fun. Get paid for that? Oh, man. Favor. Favor. Just favor. Right. I mean, she could have. Yeah. 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 Okay. Cool. That's good. Connections. That's good. What I'd like you to do now. Did anyone check the Halo class resources? Was there a MATLAB code sheet? Beautiful. I didn't forget. Okay. In the Halo, there's a MATLAB code sheet. And what I'd also like you to do is pull up MATLAB, just MATLAB for now. And under add-ons, if you haven't yet, now this is part of my welcome announcement way back at the beginning of the semester, but if you click add-ons at the top and find Control Systems Toolbox, if that is not yet installed, you should install it right now, and it shouldn't take very long, depending on the Wi-Fi. But we need the Control Systems Toolbox. Most of the stuff that I'm going to go over in the next couple slides is all on that MATLAB code sheet. You do not have to memorize how to do this code. It's all right there. Now you're going to see a lot of similarities as we go through, but we're just trying to figure out how we can use the code to do some system response. All right. So in MATLAB, in the MATLAB code sheet, if you have it pulled up, the first line, actually I don't remember it, but I think it looks something like creating a transfer function. So it's really easy to create a transfer function just within MATLAB. For example, if I had a input-output equation that looked like this, the transfer function is pretty easy. It's going to be 0.8 over s squared plus 3s plus 12. If I wanted to input that into MATLAB, we put it in like this. And it has some trouble with what's going on here. But in the MATLAB code sheet, it should say, hey, if I want a numerator, you can put a number there. If I want a denominator, you put a, it's just having trouble. These animations, they always have trouble. But notice there's no S's here. So if I'm creating a transfer function in MATLAB, I don't put any S's. I just put brackets, and like in this case, I have an S squared. So that's just a 1. This is a 3 and a 12. So it's going to know that for you when you use from the Control Systems Toolbox TF. So if I say system equals TF, transfer function of numerator and denominator, that's going to set up a transfer function there for you. So you can just copy and paste that. If I wanted to simulate a step input, the only thing I need for a unit step is just to do step of that system. So it's going to take your transfer function, it's going to give it a step input. So instead of creating a SimScape model, putting all the blocks together, everything like this. If I can have a transfer function, I just want to figure out the output based on an input. We can use this. Do you have the code sheet, the MATLAB code sheet? I like to use a live script usually when I'm doing this. Yeah, so you can just copy and paste some of that stuff. Yeah, numerator, denominator, yeah. I would just try the code and see if it works. I feel like it might be loaded. All right, you got a step. Do you have the MATLAB code sheet? The what? It's control system toolbar. So you go to add-ons. Yeah, you see it. Oh, okay. You might have it because at the beginning of the semester, I kind of had a few things you want to do. So once you have this in there, and again, this is just the only way, really, I would say, to create a transfer function in MATLAB. It's pretty fast. We can run a step input, and so if I type that in and run it, again, I like using a live script to set this up, but once I have those 4 lines of code, we can simulate, hey, if I give this thing a unit of 1 input, I can see what the output's going to be. Questions? And there's another one that we can use. Oh boy. Which is also on the equation sheet. So this is if I'm doing a unit step. This one's a little bit longer, but you can set your time. So if we run a linear simulation, you can set your time and your increments. You want it to be, small time step or large. But the helpful thing here is that I can actually change what my input is. So if I don't want just a step of 1, for my input, I can specify some kind of constant here multiplied by 1's the size of t. So this is just keeping a 1 for all of those. And we multiply it by some kind of constant. That gives us, I could say where x is equal to 20. So now I have a step of 20, and we can simulate what that output would be. Because most of the time I don't just have a unit step. So that line of code is there. Again, you can just kind of copy paste it depending on what your transfer function is. And then using this, we can put any kind of constant step in there. There's also some other fancy things. If you want to like change your plot and everything like that, you can do that here. I don't typically use it, but it's just a way. If you want to get a little bit fancy with how it looks, putting labels on it, stuff like that, you can do that. Questions up to this point? Anything not working? Yeah. Wait, if I run it, wait, why did the step go away? This? Now you run it, it should pop up with a graph. If you use that, there's the graph. Yeah. So we have 2 different ways to run a step. This one's a little bit nicer because you can specify the length of time. You can specify the size or magnitude of the input. And there's other things you can do. You can do a unit impulse. You can do a larger impulse. So I can do it in a block diagram. I can do it in SimScape. So there's lots of different ways we can run a simulation. This is just if I want to do a real quick check in MATLAB. Let me just put my transfer function in, run it, a unit impulse. What are we looking at? And then again, you can also change the size here. So you can change the size of that impulse by putting a different number in there instead of 1. But this is pretty important for us. This is also on the MATLAB code sheet. If I want to put an SSR together, the SSR needs 4 matrices. This is how you put the matrices in. So for example, A is a 2 by 2 matrix. So A looks like 0, 1, -12, -3. So if I wanted to put this into matrix form into the SSR in MATLAB, I do my row first. So this is my first row, 0, space 1, semicolon breaks up the rows. And so then it's -12, 3, or -12, -3. B is a 2 by 1. So just really be careful with this. And then when I want an SSR, we can just do system equals SS, that stands for state space, of all 4 of these matrices. You can, once you have your SSR, run the same thing, do a unit step. So either transfer function SSR, I can do a quick simulation using some of that. And this actually represents the same system. So if we ran a step input, it should give us the same output as the one with the transfer function. So that's how an SSR is inputted. And I'm not going to cover this. If we had initial conditions, that gets a little bit complicated, but there is a way to include that. So you don't necessarily need to know that. Let me go back to this. We're going to use this today. So if you want to copy and paste it, put it into your live script. Yeah, you're going to move some of the, you're going to change some of these numbers, but you're going to be able to set this up, because the last part of today is just trying to do a problem where you want to set up a transfer function, you want to set up an SSR for a single problem. So that's what we've got all the time left to do. So you can copy, paste that, have a live script ready to go, and then after that you can put in some different values. What I like to do is, we're going to transition to Simulink, but I can set up all my values inside of MATLAB on the live script. I can even set up my matrices like this. I can set up my transfer function, where then when I use Simulink, I can just pull from whatever's in the script. So if I have an A matrix here in the Simulink, I can pull from that A matrix. I can just type in A and we're good to go. So I like kind of describing everything, typing everything out in MATLAB, and then just pulling it into the Simulink space. So Simulink is block diagrams. It's like LabVIEW. So I can use a transfer function block. I can put things together. It can be a nice way just to see how everything is connected. And we're going to use transfer functions, sometimes integrator blocks, SSR, summing junctions. So you can include initial conditions, any kind of inputs. We've already gone over some of the inputs we've used in Simscape. And like we've seen before, you can change your stop time, your step size. That can help kind of smooth out your graphs. So we're not doing Simscape now. Well, we will the rest of the term. But today, we're not doing any Simscape. We're just doing Simulink. So what I want you to do is go to a new Simulink model, a blank model. And we're kind of familiar with some of these things. These are the sources that we have. We have different math operators. We have commonly used blocks. So once you have a Simulink blank model open, you can go to the library, which is, I think it's like 4 different colored squares. It's pulling up 4 different colored squares. So we're getting a blank model. Does it work? TF work? Oh, it works? Okay. Now, in Simulink, just like because Simscape is packaged inside Simulink. Let's say you want a transfer function. What I want you to do is, once you have the blank model open, double click somewhere on the blank space, just double click and type in transfer function. It should be the first. Is it the first one that pops up? So is the Wi-Fi bad today? Should be the first one that pulls up transfer function. Now there are quite a few different transfer functions. So now you can also double click. Transfer. The second one, transfer function, Simulink continuous. Yeah. There should be, if you double click, type in state, there should be a state space block, which is also under Simulink continuous. That's what we're going to use today. So we're going to feed an input in, get an output by setting up a transfer function in an SSR. There's other things. I want to talk to you a little bit about MUX and DMUX. This is specifically for an SSR. So if I have my SSR here, what MUX does is it can take multiple inputs and package them up into a way that the SSR can understand. So it can take two signals. If you've ever done like audio stuff, you've got the cable, you have the snake, it's got like 12 cables in it. That's kind of what's happening. I can take two input signals, packaging it up, so the SSR is looking for two signals. The MUX combines that. If my SSR is set up to output three different things, this is where I use the DMUX. So DMUX separates those signals. So you can, if I have an SSR and it outputs two different things, and I want to see them separately, or three different things, the DMUX is what separates that. Okay. All right. So we have an hour. I don't expect this to take an hour, but it's okay if it does. I'm going to give you a problem, and you're going to try to simulate it, not in Simscape, but Simulink. So that means creating a transfer function in an SSR. First, I got to set it up, and I can type it all out in MATLAB in a live script. And then I'm going to set up my block diagram. I'm going to have my transfer function. I'm going to have my SSR. I'm going to feed it the same input, and we're going to see if the output gives us the same result. Good? Let's try it. Can you get it? Does everyone have a transfer function block on their screen? Yeah, and you can double click the workspace, just type in transfer function. It should be under Simulink continuous. There should also be a state space. So that's what we're going to use. But it does take some work, on your end to set up both of those models. Okay. So here's your problem, and let's go for it. We've done the solenoid before. You don't even have to do full body. Full body has been done for you. This is supposed to be force. Full body has been done. They have values there. I want you to create transfer function and create the SSR. Give it that input. We're going to simulate what that output should be. How does the displacement, what kind of displacement do we see as a function of time? So instead of doing a Simscape model, we're going to create the math model in Simulink, and I can help you along the way. I want to say this again. You know what? Listen to this. This is important. What I would do, even before you make a transfer function or SSR, what you can do is type in MATLAB. In your script, you can set these. So I like to use a live script. So you can just start typing these in. You can pull from it. Instead of doing all the math yourself, let MATLAB do the math for you. So you can just set up your SSR in terms of variables. You can set up your transfer function in terms of variables, and then it can do the work for you. That's what I would suggest. So you can set up your transfer function and SSR using variables that can pull from what you just typed in. Transfer function is going to be pretty easy. SSR is where you're going to have to write some stuff. You're going to have to write, you know, set up our A, B, C, and D. That's going to take some.